Section 10.4 is covering a new conic section called hyperbolas. Now these are very related to ellipses, so we'll see how the equations relate, how the graphs relate. But I want to make a point that this is a little bit different from the hyperbolas we've talked about in our rational functions unit, where our parent function was 1 over x. Our parent function looks much different here, though the general idea is the same. We have asymptotes and we also have two different curved branches. So there will be some similarities, but the equation definitely is quite different. And part 1 of the video here is going to cover everything except for the equations of our asymptotes. So we'll look at the general form and then a bunch of information about the hyperbola, like the center, vertices, foci, etc. Okay. So to start off, we're going to compare these two equations. X squared over 9 plus y squared over 4 equals 1 is the ellipse. And if you notice the hyperbola, the only difference is that we have a minus sign. So x squared over 9 minus y squared over 4. Okay, so we know how to graph this ellipse. We can identify that our a value is 3 because a squared is 9. And we can identify that our b value is 2. Since a is with x, it's a horizontal ellipse. Okay, and our center, there's also no shift on either our x or our y. So our center is 0, 0. So if we go ahead and graph this, we can plot our center. Okay, and we can do our a value to the left and right, so 3 in either direction. We'll get those 2 points. We can do our b value up and down, so 2 in either direction from the center. And for an ellipse, we just take these points and we connect them with a nice curve. Okay. Now, what we're going to do, we don't really know what's a or b because our hyperbolic equation looks a little bit different, but just take my word for now. What we're going to do is plot those exact same points for the hyperbola. So we have the same center. We're going to plot those 4 points, so 3 in either direction to the left, 2 in either direction to the right. Up and down. Okay, now with those 4 points that you just drew, we're going to make a dotted line box connecting them. Okay, just like that. Next step, we're going to make a dotted line, which creates the asymptotes, and they're going to go at a diagonal connecting the opposite corners of this rectangle. And notice they go right through the center. Okay. The vertices on my ellipse, we can label them over here, were 3, 0, and negative 3, 0. Right, those points that were on the end. We're going to start at those points, and we're going to graph our curve going towards the asymptotes. I'm actually switch colors so it looks a little bit neater. Okay, so starting at those vertices, we make a nice curve that approaches the asymptote. And that's a hyperbola. What's graphed in green is the hyperbola. So we have the same center. Our a and b values determine that little AB box, that rectangle, and then we can graph our curve accordingly. So let's look at the standard form for a minute. Okay, you can see we've got 2 different types of hyperbolas. We have a horizontal hyperbola and a vertical hyperbola. And this is determined by the way that they open up, and it's also determined by which variable comes first. So you notice in the left-hand equation, the x minus h squared term comes first, and we're subtracting the y minus k term. In the vertical transverse axis, the y minus k term comes first. Okay, so we can label a few things based on what we did before. We still know that from the center to the vertice is A. From the center straight up on this horizontal one would be B. Now the opposite is true for the vertical. So from the center off to the left would be B. And from the center straight up to the vertice is A. And straight down would also be A. Okay. The next thing that we're going to label, these points out here are the focus points. Okay, they're kind of hugged by that curve. Just like in the ellipse, they were inside the ellipse, they were hugged by the curve. Now, because the curves are kind of flipped outwards, the focus flips out to the opposite side as well, and they're still hugged by that curve. Okay. The last thing that I want to label is from vertice to vertice. I'm going to draw that in blue. That is a distance of 2a, and this is the transverse axis. So you see below, our transverse axis in blue connects the two vertices passing through the center point. It also has a length of 2a, just like the major axis has a length of 2a. So the transverse axis is really the same thing, it's just called something different because it's a hyperbola. Now, we have these two statements. If the x squared term is listed first, the transverse is horizontal, opening left and right. And if the y squared term is listed first, being a positive term, subtracting off the x squared term, then the transverse will be vertical, opening up or down. Okay? Now, there's something that's really, really important to note. Our a value with hyperbolas always goes with the first positive squared term. Okay? This is different from ellipses. So unlike ellipses where we know that a was always the larger value, where a was always the largest value. So a always goes with the transverse axis, with the direction of our hyperbola, even if b happens to be bigger. Okay, we're going to come back to the picture and label something in 1 second, but on the next slide, we have some definitions related to the focus. So the difference of the distances from each of these focus points to any point on the hyperbola is constant. In ellipses, it was the sum. So if I had d1 plus d2, that would be constant. Here we're subtracting the distances. So the focus points are pretty crucial to the shape of these curves. Now we have these two foci, and they're located along the transverse axis, and they're a distance of c from the center. So that didn't change. We're still calling the distance to the foci c. However, c is going to be found using a slightly different formula. It looks like this: c squared equals a squared plus b squared. And that's the crucial difference. Now note, with ellipses, c squared equals a squared minus b squared. So hyperbolas, again, are slightly different. So just trying to keep track of some of these little nuances that really would make a big difference when we're trying to produce a graph. Okay, I'm going to flip back to those graphs, and let's label on our vertical ellipse, since there's less things labeled over there. Let's label our c value. C starts at the center and goes a distance all the way out to that focus point. That would be labeled C over on the right-hand side. Okay, and it's in either direction to the focuses, or foci. Okay, example 1. We're given a graph. We need to identify all the important information about it. So first thing, the center is really easy, right? It's where those asymptotes cross. It's right between the vertices. On this graph, you can see our center is that point -1, -2. If I make our vertices a little more clear, we can notice that our A value goes from center to vertice. And if we count squares, it goes 1, 2, 3, 4, 5. So A would be 5. And B is in the other direction to the dotted line. In this case, B is 3. Okay. For our vertices on our graph, we can just look at our graph. We get -1, 3, and -1. If you count down, we would get -7. However, what we're really doing is we're taking that, we have the same x value, it happens to be what h is, and we're taking our k value and we're adding and subtracting a. So in this case, it's -1, comma, -2 plus or minus 5, which would yield those two vertices. This hyperbola opens up and down, so it's vertical. Okay, so that means that our y squared term is first. It also means that the y squared has the a squared under it, because a always goes with that first positive term. So putting together our shift, we've got h and k for our center. K still goes with y, so we've got y plus 2 quantity squared over a squared, which would be 25, minus, because it's a hyperbola, we have minus, and x minus h would be x plus 1 quantity squared over b squared, which is 9. Still equal to 1, just like an ellipse. Okay? Finally, we're asked to identify the foci, and we know the foci are going to be located a distance of c from the center. C squared is given by a squared plus b squared. So in this case, we get 25 plus 9, which is 34. It turns out that c is equal to the square root of 34. So because we know the x value is still going to be -1 along our transverse axis, we're adding and subtracting our c value from our starting height of our center, which is -2. So -2 plus or minus root 34. Okay, our next example, instead of given a graph, we're given some information. We need to produce the graph. Okay, so first information says find the equation of the hyperbola with foci located at 2 plus or minus 5. Okay, if our foci are located at 2 plus or minus 5, we can graph those real quick. 2, 5, and 2, -5. That's going to tell us that our c value is equal to 5. The next statement says the transverse axis has a length of 6. The transverse axis is 2a. So 2a equals 6, we get a equal to 3. So since we know a and c, we're probably going to need b. So let's go ahead and find that right now. C squared equals a squared plus b squared. In this case, we would get 25 equals 9 plus b squared. So we get b squared equals 16. And that also means that b is equal to 4. So we have some more information we can graph here. We can graph a equals 3 and b equals 4. Since we know our center would be directly between our two focus points, it would be here at 2, 0. And we could count our a value up 3, 1, 2, 3. That's our vertice. Our other a value down 3. There's our other vertice. Our b values go 4 over to the left and right. We're going to make our little dotted rectangle, our AB box. And we can create our asymptotes by connecting the corners at a diagonal. And again, we'll go into more detail in the next video about what the equation of those asymptotes look like. But for now, starting at our vertice, our curve, you can see it opens up and down, but it's going to be pretty wide. It's going to be stretched out. And that has to do with the fact that B is larger than A. So we get the same type of curve on the top and the bottom. And there you go. And just for good practice, we're going to also come up with the equation. So we know it's a vertical ellipse, or sorry, a vertical hyperbola. So we know y squared comes first. There's no shift on our y value. We're not shifting up or down. So we have y squared over a squared, which is 9. We're subtracting. Our center is shifted to the right too, so x minus 2 squared over b squared, which would be 16, equals 1. Okay. So again, notice b is bigger than a, but that's totally fine. A always goes with the direction that your hyperbola opens up. So in this case, it's y. So there's one final example. This is related to something we've done with ellipses as well. We have an equation for the conic, but we need to complete the square, so we have the equation in standard form. So we're going to start by writing out all of the x terms first, so x squared plus 2x, and then we're going to write our y term, so minus 4y squared plus 8y. And again, I'm going to move that c value to the other side, so I'm going to get equals 19, positive 19. Okay, complete the square with respect to x. I get x squared plus 2x plus a blank. Now my value that's multiplying the y squared term, I'm going to write that, so I get negative 4, parentheses, factor it out. I get y squared minus 2y plus a blank equals 19. So we added one blank with respect to x, and then we subtracted 4 times the blank with respect to y. So if we start to fill these in, 2 over 2 squared, it gives me 1 squared, which is 1. So our first blank gets filled with 1. Negative 2 over 2 squared also gives me 1. So our other blank gets filled with a 1. So our x terms, that would be x plus 1 quantity squared. Then we have minus 4 times our y terms. It's a perfect square now, so it's y minus 1 quantity squared. And then on the right-hand side, we have 19 plus 1 is 20. Minus 4 would be 16. Okay. Now we're not quite in standard form. We always need to have it equal to 1. So we'll divide each term by 16. And finally, we will get standard form x plus 1 squared over 16 minus y minus 1 squared over 4 equals 1. So this is a horizontal hyperbola. Because our x squared is positive, it comes first. We know that a goes with the first term, so a is 4, the square root of 16. B is 2, the square root of 4. Our center is given by negative 1, positive 1. And let's start to graph this. So starting at negative 1, 1. Oops, looks like. Okay. Our a value is 4, so we're going to go 4 to the right, 4 to the left. Our b value is 2, we're going to go up 2 and down 2 from the center. We can make our box. And then we can make our asymptotes. This one looks like it's going to be a little bit skinnier than the last one we made. Alright, and from there, we know our vertices are horizontal, so my curve will approach like that. And on the right-hand side, on the left-hand side, we'll hit that vertice and approach both asymptotes. Okay, and our vertices, we can label them just based off our graph. But we also know that we started at an x value of -1 and we added and subtracted our a value of 4. And our height is 1 no matter what. So that's going to give us -5, 1, and 3, 1. Last but not least, we want to find what the foci are. So we know that c squared is a squared plus b squared, which would give me 16 plus 4, which is 20. C equals the square root of 20, which is 2 root 5. And we're adding and subtracting our c value. Just like we did to our vertices, we're going to add and subtract c from -1. So -1 plus or minus 2 root 5 with a y value of 1. Okay, that's all the information you need to provide. And the graph really helps you find all of that. There's one more problem for you guys to try on your own. You have to complete the square and then identify a little bit of the information that's asked. So the equation, ABC, the same information that we've been finding for all these types of problems. So go ahead and try that extra problem here. And we'll check our work in class.